In three-dimensional geometry, understanding how planes interact is fundamental. When two planes meet such that the angle between them is exactly 90 degrees, we define them as orthogonal. This relationship is crucial for engineering, architecture, and advanced physics applications. To analyze planes mathematically, we use normal vectors. A normal vector is a line segment that stands perfectly upright from the plane's surface. The orientation of the plane is entirely defined by the direction of its normal vector. The secret to checking if two planes are perpendicular is to look at their normal vectors. If the normal vectors are perpendicular to each other, then the planes they represent must also be perpendicular to each other. Every plane can be described by a general linear equation. The coefficients of x, y, and z, labeled a, b, and c, directly provide the coordinates for the normal vector of that specific plane. Mathematically, two vectors are orthogonal if their dot product equals 0. By multiplying the corresponding components of the two normal vectors and summing them up, we can quickly determine if the planes are orthogonal. Notice how the angle between the surfaces of the planes is identical to the angle between their normal vectors. This geometric property allows us to simplify complex 3D rotations into simple vector algebra. Let's test two planes. First, we identify the normal vectors from the coefficients. For plane 1, the normal is 2, -1, 3. For plane 2, the normal is 1, 2, 0. We perform the dot product calculation. 2 times 1 is 2, -1 times 2 is -2, and 3 times 0 is 0. Adding these gives us exactly 0, confirming these planes are orthogonal. Now consider these two planes. Plane 1 has no y component, so its normal is 1, 0, 1. Plane 2 has no x component, so its normal is 0, 1, 1. When we calculate the dot product, we get 0 plus 0 plus 1, which equals 1. Since the result is not 0, these planes meet at an angle other than 90 degrees. Often, you will need to find a specific value to make planes perpendicular. Here, we have an unknown coefficient k in our second position of the first normal vector. We set the dot product to 0 and solve the linear equation. 6 plus 2k minus 10 equals 0. This simplifies to 2k equals 4, meaning k must be 2 for these planes to be orthogonal. The most common example of orthogonal planes is the standard coordinate system itself. The xy, yz, and xz planes are all mutually orthogonal, forming the corner of a room or a box. To summarize the process, always start by identifying the normal vectors from the plane equations, compute their dot product, and verify if the result is 0 to confirm orthogonality. Remember, the relationship between planes is mirrored by their normal vectors. If the normals are perpendicular, the planes are perpendicular. This simple vector rule solves complex 3D spatial problems. Let's try a quick challenge. Look at these two equations. Extract the normals and mentally calculate the dot product. Do they satisfy the condition for orthogonality? The normals are 1, -1, 0, and 1, 1, 1. The dot product is 1 minus 1 plus 0, which is 0. They are indeed orthogonal. Thank you for watching. Generated by Vision Solve AI.